Hey everyone, it's Dr. Carroll here. It's Chemistry 40S and Chemistry 40SH Lecture 4 in Unit 4. And let me just add my notes here. Got to get my ballpoint pen going. Oh, let's use a purple today. How about that? Spice it up. So Lecture 4, and it's all about disturbance today. Disturbing a system when it's at equilibrium. And an industrial chemist who didn't like equilibrium very much, named Henri Le Chatelier, there's my French immersion for you, was the person who came up with the idea of let's find a way to not stay at equilibrium. Let's apply a stress to a system, and then the system will respond to try to minimize that stress. So that's what we're looking at in today's lecture. Have your hard copy Unit 4 booklet with you, open to page 18, and we're looking at the introduction to Le Chatelier's principle. So here in the definition, Le Chatelier's principle, if you disturb a system at equilibrium by applying a stress, the system responds so as to minimize the disturbance. Equilibrium is then reestablished with a new set of equilibrium concentrations. If you don't change the temperature, by the way, your KEQ will not change. If you do change your temperature, as we've talked about before, your KEQ does change. Another way to talk about Le Chatelier's principle is saying the system counteracts the stress applied to it. The status quo was maintained. You try to keep things the way they are, right? Like in the original High School Musical, stick with the ones you know, maintain the status quo, right? So, boy, that's my second reference to High School Musical. It must have really had an effect on me, right? And Ashley Tinsdale. Okay, so what are some stresses we can look at? The first stress is what if we change the concentrations by dumping in or taking out reactants and or products? So let's use this example here. CO2 plus H2O goes to H2CO3. And let's just assume that you're at a temperature, a high enough temperature, so they're all gas phase processes. So what can we do? We're going to look at all 6 of them in turn. All 6 stresses in turn. The first is we're going to dump in some carbon dioxide. So if we dump in some carbon dioxide, right, make this larger. Le Chatelier always goes, whoa. The first thing Le Chatelier always says is, whoa, I didn't like that there was a change happening here. I don't like change. He's like Abe Simpson on The Simpsons. He doesn't like change. He's like 95 years old, likes things the way they are. So Abe Simpson and Le Chatelier say, whoa, I don't like that you dumped in some CO2. I am going to push the equilibrium to the right. I'm going to shift to the right until equilibrium is reestablished. That's what I really mean to say. So you start at a first established equilibrium, and then you disturb equilibrium by dumping in some CO2. So the system shifts to the right, which means that when equilibrium is reestablished, well, you can't get rid of all the CO2 you put in. So the new equilibrium, which I represent by a subscript 2, is going to be greater than the first equilibrium, which is subscript 1. Okay? Because you can't get rid of all the stuff you dump in. Later on, I'll show you a mathematical reason why that is the case. Now, during that stress, some other things happen. The water reacts with the newly added CO2. So the water does decrease in concentration. So there's less H2O in the second equilibrium when it's reestablished compared to first, because it reacts with some of the newly added CO2, right? You see it over here. This is the explanation. Further, the hydrogen carbonate or carbonic acid in the, if it was aqueous, gas phase, we should call it hydrogen carbonate, I guess. The product gets more than H2CO3 You have more H2CO3 when the equilibrium is reestablished than before. So remember, these are my inequality symbols here, greater than, less than, greater than. I hope you know your equilibriums. Okay, now let's go to another example here. We're going to dump in some H2O. Well, if we dump in some H2O, CO2 is going to react with some of the H2O that we dumped in. So that is going to be less than before. H2O, well, you can't get rid of all the stuff that you put in, so it is going to be more when equilibrium is reestablished than the first one, and H2CO3 is going to be more than H2CO3 Notice in each of these stresses I'm restarting. So I'm restarting the question, getting to equilibrium, and then applying the stress. I'm not going to apply two concentration stresses at the same time. I'm going to make one stress, and then we take it from there. Okay? We could have a discussion about how people like to relieve stress, and it is stressful times. You know, like going for a walk, walking the dog, binge watching Netflix. Don't know about that one. But anyways, listening to some groovy music, that's always good. Okay, now let's start again here in the third one. I'm going to rewrite the equilibrium. CO2 plus H2O goes to H2CO3. And here we're going to restart, let the first equilibrium be established, and then dump in some H2CO3. This will be the last of the possibilities because your bosses really want you to form more products most of the time. But we have to look at all the possibilities. So if we were going to dump in some H2CO3, well then the system would shift to the left, right? Because H2CO3 will get larger, and Lechatelier goes, whoa, I don't like that it got larger. I want to try to relieve the excess H2CO3 that I dumped in. So I'm going to shift to the left. So my CO2 is going to go up. So my second CO2 is going to be greater than my first. My second H2O is going to be greater than my first. And I can't get rid of all the H2CO3 that I dumped in as I disturb the equilibrium. So there'll still be more than before. So some of you think, oh, there's got to be some sort of balance. How can they all be greater than sign? But just think that I won the lottery. Let's say I won $50. And then I gave Victor, because he's doing a good job in the course, I gave him $20. And Josh, well, I gave him $17. He's doing well as well in the course. So I still have $12 more than what I had before. So all three of us have more money than before. So it's not like someone has to have less money and someone has to have more. I mean, if you want to talk about that, we could talk about the whole capitalistic and socialistic economic of the universe, but that's a different course. Anyways, so I'm going to, by the end of this, I'm going to try to get everyone's names in here, okay? All I have to do is say Anna, right? Because there's like 15 of you who are named Anna, and the other 15 wish your names were Anna, right? Okay, I'm getting a little silly. So now let's scroll down here and go to page 19. Okay, so now we're going to restart. I'm going to rewrite the equation again. CO2, oh, I have this stylus, this little pen that I write on, and sometimes I write, rather than on my tablet, I write on the mouse pad, and it doesn't work. CO2 plus H2O goes to H2CO3. So let's restart, but let's take out some of the CO2. So remove a bit of the CO2. We take a bit of the CO2 out, and then the system is going to go to the left. You try to replenish, right? Replenish means to bring back, to recover the stuff that you took out. So if I try to replenish the CO2, I can't get all of it back, but I can try. So the new CO2 concentration is less than the initial. It might be slightly less, but it's less than when equilibrium is reestablished. The H2O is more because I didn't take any of the H2O out, and the H2CO3 is less. Okay, so if I remove some CO2, the system shifts to the left, and these are the relative concentrations of the reactants and products. We start again in E, but this time we're going to remove some H2O. If I remove some H2O, system shifts to the left. CO2 gets larger than it was before, right? So it's built up. H2O, well, there's less than before because I can't regain all the H2O that I took out. Can't regain all my past glory. And the H2CO3, the second one, is less, so it goes to the left. So all of those are correct. Okay? Let's go down here to the final of the possibilities. What's our equation again? CO2 plus H2O goes to H2CO3. And this time we're going to restart, but we're going to remove some H2CO3, okay? And this is the one that would happen most often in industry. You just get to equilibrium and then your boss says, no, I don't want to get to equilibrium. If I'm a carbonic acid factory, I don't want to lose carbonic acid back to the reactant. So as soon as you get to equilibrium, you start taking some of it out, and then Le Chatelier shifts to the right. Goes, whoa, I don't like that some was taken out, so I'm going to shift to the right, which will give me more H2CO3. And that's what you want to have happen. You want to be, you can be close to equilibrium, but you don't want to be at equilibrium, because then the H2CO3 is going to shift back to the left. So the best is, as you're getting that H2CO3 forming, put it in a bottle, put it on a truck, and sell it for maximum profit, right? There you go. So the CO2, when equilibrium is reestablished, is less than CO2-1. The H2O2 is less than H2O1, and the H2CO3 is also less than H2CO3-1 because you've taken some out. And now this reaction is not going to happen forever. You need your starting materials. You need your CO2 and H2O. So those are examples of dumping in more moles or taking in moles out, and over the lots of worksheets for you to try, you'll become experts on this, which is a common stress used in Le Chatelier's principle. Okay, so that's the first one. Now, on to the second stress, which is adding a catalyst. And you'll like this one because adding a catalyst doesn't cause a shift. It just allows the reactants to form products and the products to bounce back to reactants at a quicker pace. But it doesn't mean you got more products than reactants relative to before you put the catalyst in. So you wouldn't really add in a catalyst to try to change the relative percentages of reactants and products. Rather, they change the rate. So adding a catalyst will not shift the position of equilibrium. No shift. Okay, stress number 3. This is the trickiest one because KEQ itself changes. October 29th. Really? I don't think so. Maybe there was once in October 29th. Temperature change. And there's books that makes things way more complicated than they have to be. What I'm going to do is just pretend heat is like a chemical. So if the temperature goes up, the moles of heat goes up. And if the temperature goes down, the moles of heat go down. So here's an example, and this in your hard copy book is near the bottom of page 19. So I got liquid water and water vapor at an equilibrium. It's an endothermic process, which is obvious, right? The liquid water, being the system, absorbs energy from the surroundings. Let's say there's a mole, it can absorb 68.3 kilojoules. And so endothermic, delta H is positive. If the temperature goes up, the system shifts to the right. It's like I'm making the 68.3 kilojoules, this heat, more important by increasing the temperature. And Le Chatelier goes, whoa, I don't like that. It became more important, so I'm going to shift equilibrium to the right. And your KEQ is going to get larger. Your KEQ is really just the pressure of H2O gas or the concentration of H2O gas. So it also makes sense, you know, if you have a closed flask, if you increase the temperature, you're going to have more composition richer in the vapor phase than in the liquid phase. So for endothermic cases, if temperature goes up, the system shifts to the right. If temperature goes down, well, then you're sucking out some of that heat, so the system's going to shift to the left, and we'll get less H2O gas. Your KEQ will get smaller. Okay, so that is one of the two cases for temperature changes and how temperature affects equilibrium. The other case is exothermic. And we have here 2SO2, this is the bottom of page 19, 2SO2 plus O2 goes to 2SO3 plus heat, right? So this is exothermic, delta H of the reaction is negative. If temperature goes up, it's like the heat's getting more important here, right? But it's on the right-hand side, so the system is going to shift to the left. So if you want less SO3 to be forming as equilibrium kicks in, kick up the temperature, and then you'll get more SO2 and more O2. If you want more SO3 forming, then take your flask and dump it into an ice bucket or something. Have an ice bucket challenge, and then the system is going to shift to the right. So KEQ goes down as the temperature goes up, because you'll have less products than reactants, and KEQ goes up as the temperature goes down for exothermic cases. Okay, on to page 20. This delta NG, I think we aren't going to deal with it. There might be one question on a worksheet about it. It's just in a balanced equation, you add the gas mole coefficients on the product side and subtract from that sum the gas mole coefficients on the reactant side. It's something that you'll learn about in your next chemistry course. Okay, so on page 20, I want to look at stress number 4, which is change in pressure, and there's a few changes of pressures we can look at. Okay, first of all, you could just dump in more of a gas, so that changes the pressure for a given reactant, but that's just like stress number 1. You could also just dump in an inert gas to increase the pressure of everything in the flask, but that's not going to cause any shift because there's no reactions there. The real stress we want to look at here is change in pressure. I'm going to add this in here, due to volume of flask changes. And as you remember from Boyle's law in grade 11 chem, pressure goes up, volume goes down. Pressure goes down, volume goes up, constant temperature, number of moles. So that's what we'll look at here. So there's two possibilities. If the pressure increases by decreasing the volume, right? So you're packing in all the reactants and products into a smaller container. The system shifts from the side with the more molar gas coefficients to the side with the less molar gas coefficients. Because the more gas there is, the more pressure is going to be exerted. So Le Chatelier goes, whoa, I don't like that pressure is increasing. I want to counteract that increase in pressure. So I'm going to go to the side where there's less gases possible. And conversely, if the pressure goes down, Le Chatelier says, whoa, I want more vapor to form, so I'm going to shift to the side with more gas mole coefficients. So from the less molar gas side to the more. Okay? See, students sometimes think, oh, they want to simplify too much. And they say, well, if I increase the pressure, I go to the right. If I decrease the pressure, I go to the left. You can't do that. You have to look at each individual balanced chemical equation. Look at the gas mole coefficient sums on either side, and then make your choice based on that. So let's look at the first example, which is near the middle of page 20. So here I have a physical equilibrium between H2O liquid and H2O gas. The delta Ng is 1. Find 1 gas mole coefficient on the right, 0 gas mole coefficients on the left. And so if the pressure goes up, then the system is going to shift to the left, because I have 0 gas mole coefficients on the left, 1 gas mole coefficient on the right. So if I increase the pressure by squeezing things down into a smaller container, then I'm going to be less rich in my H2O gas. I'm not sure about that. Let's strike that last statement. That's an irrelevant to what we're talking about here. If the pressure goes down, then the system is going to shift to the right. So if we're in a bigger container, the system will shift to the right. Okay. This vacuum pump, don't worry about that. You can boil water, make tea if you want. I don't know why that's there. Okay. Second example, we got SO2 gas plus half O2 gas goes to SO3 gas. So we have 1.5 gas mole coefficients on the left and just 1 gas mole coefficient on the right. So if I increase the pressure, the system says, wait, I want to go to the less gas mole coefficient side, so I want to shift to the right, because I got 1.5 gas mole coefficients on the left and just 1 on the right. And that's what happens. If I decrease the pressure, well, you just do the opposite. You want to get more gas mole coefficients. So pressure goes down, the system shifts to the left. Here's example 3. N2 gas plus 3H2 gas goes to 2NH3 gas, the Haber process. So if I increase the pressure, the system shifts to the right because there's 4 gas mole coefficients on the left and just 2 gas mole coefficients on the right. So that's what happens. If I decrease the pressure, then I shift to the left. Now example 4 is an interesting one because there is no shift whether I increase or decrease the pressure because I got 2 gas mole coefficients on the left. Right, the sum is 2, and on the right the sum is 2 as well. So hydrogen plus iodine gives me 2 moles of hydrogen iodide. Whether I increase the pressure or decrease, I am not going to shift the position of equilibrium. Now, stress number 5, volume change, but I've really bundled stress 4 and 5 together, right? Some books, I only write it like this because some books try to separate them, but if we're talking about Boyle's law, pressure volume, then the same rules are applying. As soon as you see a volume change, convert it into pressure changes and use the rules associated with stress number 4. So here I got PCl3 plus Cl2 goes to PCl5. And so I got 2 gas moles coefficients on the left and 1 on the right. If I transfer this mixture to a larger flask, the volume is going to go up. Well, if the volume goes up, the pressure goes down, and the Chatelier is going to shift to the left because we were trying to regain the pressure that we had before. And obviously, if volume goes down, pressure goes up, and then we're going to say, whoa, I got too much vapor there, so I'm going to go to the right. I'm going to shift to the right. So from 2 gas mole coefficients to 1. Example 2, I just scrolled in on the bottom there, and the reason I did that is to show you sometimes you have mixtures of phases. You don't all have the same phases. So I got 5A gas plus 9D liquid goes to 6E aqueous plus 3G gas. So if I increase the volume, then the pressure goes down, and I want to go to the side with more gas mole coefficients, right? And that would be to the left because I have 5 gas mole coefficients on the left and just 3 on the right. So volume goes up, pressure goes down. We are going to shift the system to the left. Volume goes down, well, volume goes down, pressure goes up, and I'm going to shift to the right because I'll go from 5 gas mole coefficients to 3. Okay, I don't know why it said that thing there. Scribble that out, that shouldn't be there. So, now for you to practice, not for marks yet, I mean that's coming, but practice, you can now do page 16 and 17. So do page 16 and page 17, and that is worksheet Secretariat, a famous racehorse. And then one of my strange memes, right? Then can we do all of Seabiscuit? It looks like that we can. So that's page 21 and 22, 23, and 24. Right. So do page 16 to 17 and page 21 to page 24. On EDSB, I gave the answer keys for these, but try to do them all first and then check the answer key. The answer key is also on our website, which I sure the heck hope you know by now, tinyurl.com /vmchem, go under the Unit 4 sidebar and find something that says all answer keys for Unit 4. So try those out and have fun with it. I hope it doesn't stress everyone out too much, because we're looking at disturbances with Henri Le Chatelier. Okay, and we will get together again quite soon. Bye for now.